Here we're going to describe the Levy's constraint search formulation, which is going to be really useful to redefine this universal functional of the electronic part in the Hamiltonian as a function of the electronic density here. It was proposed by Levy first and later by Lieb in 1879. And it was they defined this functional, this universal functional, in the following way. It's a minimum of this contribution here, which is the average of the kinetic energy of the electrons and the electron-electron interaction. And the minimization process is done in the following way. The minimization is done over the normalized anti-symmetric wave function here, which yield that electronic density, which yield the fixed electronic density. So for a given density, you fix the density and minimizes with respect to the wave function given that density. And the minimizing wave function is defined in this way, that of course is going to be a functional itself of the electronic density, and we can write in this way. Therefore, this one here we can write in this following way, where this one here is going to be the wave function that minimizes that for a given fixed electronic density. And therefore, this one is going to define a functional which is going to depend on the electronic density. This way of defining this universal function of the electronic contribution in terms of the electronic density is more straightforward than the Hohenberg-Kohn definition, as it does not require the existence of the external potential associated to the electronic density. Here we are not mentioning anything on the external potential. Of course, we need that in order to minimize the whole Hamiltonian, but that's going to be later. That one here is defined on a larger set of n electron densities. Here these are n electron densities coming from these anti-symmetric wave functions. And this way, these densities are called n-representable densities, because the densities we are considering here when we are saying, okay, we fix the density and you minimize with respect to the wave function, the kind of density you're fixing are those that are n electron densities coming from an anti-symmetric wave function. We are not care if this density, we don't care if this density can be possible density coming from any external potential here. So once we have that, once we have this way of defining this universal function on the electronic density, then we consider the variational property. Okay, we know that the ground state energy is just the minimum of the total Hamiltonian. That's a variational property. That's a minimum, and then the minimization of the wave function of this, the total Hamiltonian. We have here the kinetic energy of the electrons, the electron-electron interaction, we have the interaction of the electrons with an external potential here. Okay, and now here, this minimization process, we are going to do that. This minimization, we are going to decompose that minimization over this wave function here in two steps. Okay, first we are going to do a constraint minimization over C given a fixed density n. So we fix n density and we minimize with respect to the wave functions that have that density. And second, we minimize with respect to n. We do the minimization over n. So we consider different n electronic densities and we take that minimizes. Okay, we separate therefore this minimization over this wave function in two different steps. One, a constraint minimization of C for a given density, and then second, you minimizes with respect to electronic density. And then we are going to separate that contribution to the total Hamiltonian in two different contributions. One is this one, and that's associated to the universal function of the electronic contribution. And the second one is just depend on the external potential. And if you split this average here in two contributions, you have, this is the first one coming from the first two terms that depend on the electronic properties, and then you have the second one, that's the one associated to the external potential. You can easily see that it just depends on the electronic density. Okay, here you can see we are separated the minimization that we have decomposed in two parts. Okay, and as you can see here, the first part here, this is just the universal functional we have just previously defined. This is the universal functional on the electronic density. And then we have that this second term here, it's also a function on the electronic density. Okay, it's also a function on the electronic density. So we have, therefore, in this minimization process of the total Hamiltonian, we have that the total Hamiltonian is split in two terms. One is the universal contribution associated to the electronic part. It's a universal function of the electronic density. And you have that the other term, which is associated with external potential, it's also a function on the electronic density. And then, in order to calculate the minimum, the ground state energy, the last step you need is just to minimize with respect to the electronic density. You have to minimize this functional of the total Hamiltonian, which includes two terms, the universal functional that just depends on the electronic contribution. I mean, it's universal in the sense that it does not depend on the external potential, and then you have another term that just depends on the external potential. So the minimization on the end here is going to give you the ground state energy. So we know, according to that and following that Levy's constraint search formulation, that helped in order to redefine that universal functional of the electronic contribution, and it's also giving us a way to get the ground state energy once we have that universal functional. Of course, that's giving us a guide to get that universal functional. However, it's not giving us any prescription of the precise expression that this universal functional can have. And of course, that remains to do. What could be a precise description of this universal function? It's easy to get, because in case we have so, then we could solve quite easily, just doing the minimization procedure, we could get the ground state energy of any electronic system.